Our final method for solving systems of linear equations is going to be called the elimination method. The purpose here is to line our equations up, and then basically it's combining like terms. We'll get to an example and I'll kind of explain the math that's going on behind the scenes, because otherwise it just kind of seems like a magic trick. All right, let's start simple where there's things all ready to eliminate. So what's going on here? The idea with the elimination method is I'm going to combine like terms straight down. But how is that allowed since I'm adding stuff from different equations? All right, well, let's pick apart based on things we know from math. What does the equal sign mean? That means left equals right. They should have the same mathematical value, or at least that's what the symbol's trying to tell us. So what this is saying is 3x plus 2y and 4 from the first equation are equal. Okay, so you know that little thing where we're allowed to add the same thing to both sides of an equation? Well, what this sentence is saying is that mathematically these are the same thing. So in my second equation, what we have to pretend is happening is I'm adding 3x plus 2y like an algebra step. And on the other side, I'm adding 4 like it's an algebra step. And I'm allowed to do this because 3x plus 2y and 4 are equal. The reason it's called elimination is let's actually add 3 plus 3 is 6. Negative 2 plus 2 is 0, 0y. That's eliminated. Negative 4 plus 4 is 0. We didn't mean to eliminate that, it just kind of happened. So this is why it's called the elimination method. 0y is 0. It is unnecessary for the problem anymore. All right, so what's left is 6x equals 0. Divide by 6. Our answer is x equals 0. Now, remember, our solution should be an ordered pair, so I should plug that back into one of the originals. 3 times 0 is 0. Essentially, what's going to come out of this is y equals 2. So my ordered pair for my final solution is 0, 2. And that should be where the lines cross. So something gets eliminated. All right. Now, other problems we're going to have to set ourselves up for this. So let's look at another example. Here we go. Looking at this mathematically, nothing is going to cancel out. Okay, so what I need to be able to cancel things out is I need matching coefficients. All right, we can modify our equations using algebra steps to try and get matching coefficients. Okay, so how can I make negative 10x and negative 5x equal? Well, if I multiply this equation by 2, then they will be. So this equation is no longer necessary to find our solution to the problem, because this equation is the same, and it's going to let us eliminate. All right, now last time I added the equations together, but if I add negative 10 and negative 10, I'm going to get negative 20. When I have two of the same things, subtracting is what gets me 0. So now I'm going to subtract the equations. Negative 10x minus negative 10x is 0x. That's what we wanted. 3y minus negative 12y minus a negative turns into addition. 3 plus 12 is 15. 1 minus 46 is negative 45. So one layer of confusion here, possible confusion, knowing when to add or subtract. If something's not going to cancel out by adding, you have to subtract. 0x is what got eliminated. Divide by 15 to get y by itself. Negative 45 divided by 15 is negative 3. Plug that back into one of the originals. I'll plug it into this one. Negative 10x plus 3 times negative 3 equals 1. 3 times negative 3 is negative 9. Add 9 to both sides. Negative 10x equals 10. Divide by negative 10, and we should get our answer. X equals negative 1. Now we have our x and our y. Write that as an ordered pair, and we have our final solution. That would be the point that these lines would cross at. You might notice elimination takes a little bit less writing and a little bit less work. That's true if you have good numbers for it. Substitution always works, but in a problem like this, substitution is going to make you deal with fractions more. So they have their ups and downs. Okay, here we've got a word problem that demonstrates when elimination might be useful for an application. What I want you to kind of think of here is this is the idea behind triangulating information. We have a couple of data points, and we're able to use those data points to figure out missing information. Okay, so one data point is that we have 2 business locations. The first location rents 5 large vans and 2 small vans for 235 grand. The second location, location B, rents different numbers of them with a different total price. With this information, we're able to figure out the cost of each. So location A's equation, 5 large vans and 2 small vans adds up to $235,000. So L and S represent the cost of each. Location B has 2 large vans and 3 small vans for a total cost of 160 grand. Okay, looking at this, you might already be thinking to yourself, what am I going to multiply? Because we're going to try and do elimination. Well, 2 doesn't multiply up to 5 evenly, and 2 doesn't multiply up to 3 evenly. So we have to multiply both equations. What's the smallest number we can get? Well, I'm looking at this, and I'm seeing 2 and 3. They can both go into 6. So I'm going to multiply the top equation by 3 and the bottom equation by 2, and that'll get the small van numbers to match. So now I'm going to be working with 15L and 6S equals, quick math, 705,000. 4 large and 6 small gives me 320,000. All right, now if I subtract, 6 minus 6 is going to be 0, so they'll be eliminated. 15 minus 4 is 11. 6 minus 6 is 0. That's what gets eliminated. That's what we wanted. 705,000 minus 320,000 is 385,000. All right, let's cover up that glare so you can see the equation quick. Again, sorry about that. 11 large vans equals $385,000. Divide by 11 and we figure out the cost of a large van. All right, so a large van costs $35,000. Now that we know the cost of a large van, we can figure out a small van by using one of our other equations. I'm going to use the one with the smaller numbers. 2 large vans, 2 times 35,000 plus 3 small vans equals 160 grand. 2 times 35,000 is 70,000. And I'm going to subtract that on both sides. There's 90 grand left. Divide by 3, and we get the price of a small van. Small vans are 30 grand. All right. Now I'm not going to write my answer for this one as an ordered pair, because the answer to the question is how much is a large van and how much is a small van. That doesn't necessarily need to be on a graph. All right. So that's an example of how elimination might be used for a word problem. We have 2 data points, and we're able to use those 2 data points to solve a system. Okay, so think about this in a different sense. If I give you a few locations and then I'm able to use like radio towers to figure out where someone's cell phone is, I can use that information to figure out where exactly they are based on how far away from each individual radio tower they are. It's kind of neat. It's kind of interesting. There's more useful examples of this, but the more useful examples actually start to use some trigonometry. So this won't get as cool as it can be until advanced algebra for you. Now I say cool, but I think it's interesting. You can figure out where stuff is without actually knowing where it is just by having a few vantage points. So, yep. You can also look at things in the distance and travel. It's all kind of cool. Triangles are neat. You have no idea how much they can do for us in math. So, maybe that's the motivation to learn this and get good at it so you remember in the future. You remember Mr. Marsall told you about these cool things. They'll show up in a couple of years. All right, that's it for lesson 5.3.